Okay, moving on. Next we're going to discuss chapter number 13 in our textbooks, which covers the policy gradient theorem and policy gradient algorithm. Specifically, the basic algorithm will be reinforced algorithm, and then we'll see some enhancement to that algorithm. By the way, this will build us later towards ectocritique algorithms. The main motivation behind policy gradient algorithms, we've seen those algorithms previously when we discussed those in the context of multi-armed bandits, right? Where in many cases, trying to learn the value, the state value or the action values for all of the states in our state space might be an overkill. We don't really need those. In many cases, we just care about the optimal policy. We would like to compute the optimal policy. So policy gradient algorithms, or as we previously called them, policy iteration algorithm, when we discussed those in the context of multi-armed bandit, allows us to quickly converge on the policy, and in many cases that might be much faster than trying to converge on the values, right? Using a value-based approach, right? And for instance, you can see an image here where a policy might only say, hey, listen, you need to go left or go right, while a value-based approach might say, well, I still need to converge or calculate all of the Q values for all of the possible actions in my action space. And obviously this can give you the idea that policy gradient algorithms might be more effective if your action space is very large, specifically compared to action value-based approaches, Q-learning approaches. Okay, so indeed today we're going to describe our policy as using a function approximator, as a parameterized function approximator, and we're going to compute gradients in our policy that hopefully most improve the performance of the policy in the given state space, and take a small gradient descent, or in this case it will be gradient ascent if we're trying to look at the rewards, sum of rewards, towards improving our policy over time and hopefully converging on the optimal policy. So some notation that we're going to use today. The policy is now a parameterized function, so we'll call it, and also this is also from the textbook, we'll define it as pi with some given set of tunable parameters. This is the theta vector, and this will be a function of action given a specific state. This will return the probability of taking a specific action in a specific state. So this, in this specific example, or this specific notation, refers to a soft policy, right? If you remember, a soft policy provides a distribution over the action space as opposed to a hard policy. However, actually policy gradient algorithms can also, we have some that do use hard policies, right, such as deep deterministic policy gradients. So there are some policy gradient theorems or policy gradient algorithms that work on deterministic policies, and we will cover those later. But for the sake of at least this topic, we're going to discuss soft policies that are represented as follows. So for performing policy gradient learning, we require a differentiable policy. And again, this is something that we've seen previously in the multi-armed bandit case, where in order to make our policy differentiable, we use the softmax activation over, I think at that example, you can go back to that lecture and see that there we defined our policy using some activation or some score that we assigned to each one of the actions, and then we added the softmax function on top of these scores, and then that provided us with a differentiable function that was differentiable with respect to the scores, and allowed us to tune these scores for each one of the actions. So indeed, our policy is assumed to be differentiable with respect to theta, to the tunable parameters. For instance, a deep neural network where our tunable parameters are the set of weights and biases. And this, you can see an example down here. I guess in this case, the deep neural network provides us with a distribution of all of the actions. Again, this specifically represents a soft policy. But as I said previously, we have examples, or we have algorithms where the approximation is just with respect, or outputs a specific action. These are deterministic policies. But for today, let's just assume that we have a soft policy. Then we're going to use capital J to represent some policy performance measure. What would be a policy performance measure in a specific state space? That might be just the expected, that will be the expected sum of discounted rewards. Again, of course, this is dependent on the initial state. So we'll assume a specific initial state where we start all the trajectories from. But everything that we're going to discuss today is also can be generalized to the case where the initial state is just, there's a distribution over the initial state. Yes, question?
How does J here differ from a Q function which also learns the expected sum of discounted rewards?
So, specifically, so a Q function is dependent on an action, right, at the end of the day. So it is somehow policy dependent. Actually, so this is also policy dependent, right? So we have a specific theta assignment that defines a specific policy. So the main answer here is that we can write it with a Q function over the expected action. If we assume a soft policy, it will just be a more complicated notation, right? A longer notation we can write, and I'll actually, once we'll do the derivation for the policy gradient theorem, I'll show you how we can actually write it using a Q function. And we'll expand and try to simplify some of the terms there and see how we can get to a good approximation of the gradient of J. The main reason I'm using J, and the textbook uses J, is just the compressed representation for Q for the initial state and the expected action and so on. So it's just a compressed representation. It is the same, okay? So J, given a specific policy that is defined by the tunable parameters theta, is a scalar policy performance measure, so it returns some value, which represents the expected sum of discounted reward with respect to the policy parameters. Okay, with respect to the policy that is defined by these policy parameters. So it is the Q values, but the Q value for the initial state, just a compressed representation of that value, or way to define, to represent that value. Okay, so how do we improve the policy over time? So we're going to use stochastic gradient descent, where we'll update our policy, which is defined by the policy parameters theta, based on the gradient in J. What is the gradient in J? It's how to change our tunable parameters, theta, in a way that increases J, in the direction that increases J by the most, right? And this is exactly what we want to do. We want to update our policy to increase the expected sum of discounted reward expected by following that policy. And in this case, we're going to use an approximation of the gradient of the J, because it's, well, as we'll see later, it's something that's difficult to define in a closed form expression without knowing, of course, the model, and we don't assume to know the model. So we're going to use a stochastic estimate where the expectation approximates the gradient of the performance measure. This is our J, the definition of J. All methods that follow this general scheme we call policy gradient methods. These might also include value approximation for normalization. This is known as the baseline for normalizing the gradient, or not exactly, it normalizes the gradient, it actually normalizes the expected sum of discounted reward. I'll discuss this later on under this topic, and we'll see how to use reinforce with a baseline. And again, this will also include some value approximation. And then there's another class of methods which we'll discuss later on, which use, again, both an approximation for the policy and for the value function, but we use the value function in order to refine or to compute a better gradient in J, in a better policy gradient. And these better, I mean more accurate, not normalized. I'll explain the exact difference later on. But methods that also include value function approximation in order to compute a better or to have a more informed gradient in J are known as actor-critique methods, and we'll cover those later on. These are state-of-the-art at the moment, at least. Okay, we'll see those later on. These are usually simple extension to the reinforced algorithm that we're going to cover today. So what are the main advantages of using a policy gradient algorithm? So this is actually something that we've seen before when we discussed dynamic programming in known MDPs, in MDPs where we know the model, and also in the multi-arm bandit case. So policy gradient or policy iteration methods, right? This is an extension of the policy iteration methods, or can be thought of an extension of the policy iteration method under some conditions which we'll discuss later. In these methods, the policy convergence over time, as opposed to an epsilon greedy value-based approach, for instance, that must guarantee some exploration or some continual exploration, which in many cases prevent us from converging on a policy. So we don't have that issue in policy gradient approaches. They naturally apply to continuous action space as opposed to Q-learning approaches, right? So for Q-learning approaches, we need to learn a specific Q value for each state and action pair. So we have to iterate over all of the possible actions. And this is not possible if your action space is continuous. You have actions from the range -1 and 1. This is actually pretty common in robotics. And also other, I don't know, which domain? Can you think of relevant domains? You have to invest money maybe, or... in any case, yeah, it's... so for instance, in the Mojuku domain, you'll see a lot of continuous control. Autonomous driving domain, you'll also see a continuous action space. And you will implement, I think, one continuous control algorithm, and specifically a actor-critique algorithm later on in the course. Next, in many domains, the policy is actually simpler to approximate. Now, this is a bit hand-wavy, right? But we did see this before, where the policy converges much faster than the values. This is not always the case, but many times it is the case, or at least, I don't know, from my experience, maybe for your experience as well. And by the way, you can try this in your home assignments implementation. And you can see that in many cases the policy indeed converges faster compared to the state values. And as I said before, in most cases we actually care about the policy and not specifically about the state value. Next, choice of policy. Next, doing policy gradient allows us to initialize a specific policy that might be something that we know works pretty well. For instance, I guess for the traffic signal control domain that we work on in my lab, it's pretty efficient to initialize our policy with some known fixed time controller, some common cycle that is used in existing traffic intersections, and start from that point and then just improve over time, hopefully improve over time if we do meaningful learning. So it provides us, the policy gradient algorithm provides us with a pretty effective way of injecting prior knowledge regarding a good policy. And finally, if we use policy gradient with stochastic policies, soft policies, it can allow us to converge on actual soft policies with some distribution that is not as, it doesn't always return a specific action, right? Like hard policy usually does. This can be very useful in games with imperfect information, where the optimal play is often inherently random. For instance, if you're playing poker, you don't always want to perform the same action given the same state that you have, because in poker, for instance, in many cases you want to bluff even if you have a weak hand. So normally you want to maybe fold and not raise or increase the sum of your bet, but you don't always want to do that. That might be the optimal action in a one-shot game, but over repeated games this is not always the optimal action, because if you use a hard policy, for instance in poker, then you let your opponent know about your state, and this is something that's not advisable when you play poker. Apparently, I'm not a poker player, as far as I know. So indeed, this is another advantage of a policy gradient, but it's not actually an advantage of policy gradient, it's more of an advantage for converging or defining soft policies. And the policy gradient approaches allow us to actually converge on soft policies, right? And diverse or non-deterministic soft policies.